it's my great pleasure to introduce the new speaker. The second speaker of the day is Gabriel Girard. Gabriel Girard is a staff scientist at the Sherbrooke University in Canada. He also holds a little affiliation at DEP from TS5. So Gabriel obtained a double PhD in computer science from the University of Sherbrooke in Canada and the University of Nice Sophia Antipolis, and under the direction of Professor Maxime Descoteaux, Kevin Whittington, and Professor Rachid Derish. In 2016, Gab received a Marie Sklodowska-Curie EPFL Fellowship, hence he moved to Switzerland and worked as a postdoc in the Professor Jean-Philippe Stiron lab. And you may know him already, or several of you may know him already, because Gab is a CIBM alumni. He joined the research community at the CIBM Signal Processing Shift EPFL section in 2018, when he worked there until 2022 when he moved back to Canada. So the primary research focus of Gabriel is white matter reconstruction using diffusion MRI. And in today's talk, we were talking about how to assess the predictive capacity of diffusion MRI tractography for white matter structural connectivity estimation. And the floor is yours.
Thank you, Ella. Thank you for the invitation to present, to speak about this work. So I will be presenting 3 papers that I've been working on during my time at CIBM, in the research community at CIBM. All of the work are related. The topic is validating tractography and especially connectivity. So before I get into the work, I just wanted to picture an overview of where the work I will be presenting is in the domain. So what you see there is an image of diffusion MRI. Each image is sensitive to the diffusion of water in one specific direction. And from this, we can derive, for instance, the diffusion tensor imaging model, which is a Gaussian approximation of the water displacement. We can also do microstructure imaging, local voxel-wise modeling. But for the purpose of this talk, the most interesting object is this fiber ODF here, which is a spherical histogram of the orientation of the axon in every voxel of the brain that we do. And from this, we can use tractography to build a set of 3D lines that we call streamlines, millions of them approximating the trajectory of the white matter in the brain. One thing that we can do from this is to extract white matter bundle. You can see the corticospinal tract in blue, the corpus callosum bundle in red, for instance. And we can also summarize this set of millions of streamline into this 2D object, which we call the connectome or the connectivity matrix, using a parcellation of the gray matter. So here, all the rows are gray matter region, all the column of gray matter region, and the intensity of this image corresponds to an approximation of the connectivity derived from diffusion MRI. And you can see that as an adjacency matrix and do network analysis on this object. So what I will be talking today is really those 3 key steps from the diffusion data to the fiber ODF, including the pre-processing, and then the tractography algorithm to get the set of polylines, and finally the filtering and tuning of those streamlines to build a summary or a fingerprint of the connectivity describing the subject white matter. So really those 3 key steps. And the motivation for this work was this paper in 2017, which was the result of a challenge organized for challenging tractography. And the idea was to build, what they did actually is to build a synthetic phantom, synthetic signal from a set of a real bundle in the human brain. And they asked the community if they could figure out which bundle was used to build the data. And the community submitted a lot of reconstruction, and overall 46% of the streamline that were submitted were wrong, and 36% of them were not connecting, were connecting unconnected regions, so were not existing in the ground truth, and 10% did not connect anything. And overall, tractography produced 4 times more false positive connection than connection that do exist in the data set. And to quote the author, this demonstrates the inability of current state-of-the-art tractography algorithm to control for false positive. So at this point, tractography was a little bit challenged, and we wanted to know on different data sets how tractography performs, essentially. And the main problem that was highlighted in this work is the bottleneck problem of tractography, where you can see here that in the ground truth data, you have up to 5 bundles that merge in a single voxel of the image, while if you look in the diffusion orientation, you have 1 or 2 orientations. So you have multiple bundles co-aligned in the voxel. And to put it in a simple example here, you have 2 bundles that merge in this middle section here. Just the mouse. And so here you have a single fiber population. This is fine, this single bundle. You have this crossing area at the top of the bundle, but in the middle you have a single peak. So you could imagine tractography following those directions here and being a little bit confused if it needs to go back on the right side. So tractography is a little bit simplistic in this way. And most tractography algorithm will give you the 2 sets of bundle, the crossing bundle and the kissing bundle. 2 will likely be true, exist in the data, but 2 will also be false, and you will create 2 false positives doing so. So the plan for today's presentation is split in 3 parts. The first part will be using evaluating tractography using macaque neuronal tracings, which is probably one of the best ground truths we have for validating tractography. In the second part, I will be discussing the use of a large-scale synthetic data set that we call the DISCO Phantom to challenge tractography. And finally, I will be discussing using test-retest data to assess the reproducibility of the connectome estimated with diffusion tractography. So this is the first paper. The title is on the cortical connectivity of the macaque brain, a comparison with diffusion tractography and histological tracing data. So this was initiated in 2018 after a work by Roberto Caminiti and colleagues, where they essentially look into the literature, over 40 years of literature on track tracing data, and summarize what was reported in the literature in terms of connectivity. So what we see here in light green is regions that were reported connected in the literature, and in dark green, regions that were not connected by track tracing. And this is a limited set of regions. There's 59 of them, better matching what the author of the paper was reporting. So it's mostly located in the frontal and parietal part of the macaque brain, and mostly there's 18,000, 17,000 pair of region, and 1/3 more or less is reported connected by track tracing. So now the question is, can tractography using diffusion data can classify the pairs of ROI to obtain this subject on the right? And to do that, we use the best ex vivo diffusion data we could find. It's extremely high resolution and very good quality data that we had, and we did the same parcellation on this very brain to match with the matrix that we had before with it from the track tracing. And to build the connectivity matrix, we use a standard way to do that, especially in neuronal tracing, and we counted the number of streamlines connecting 2 ROI over the total number of streamlines connecting any of those 2 ROI. So it's a kind of volume fraction or fraction-weighted connectivity estimation. And now we have a weighted connectome, and we need to binarize the subject to be able to compare with the ground truth. So the question is, what is the optimal threshold? And one way to do that is through a ROC analysis. What you see here is this matrix thresholded at a value superior to any value in this matrix. So essentially what I'm saying here is nothing is connected. And if I do that, everything that is in gray is correctly classified, right? These are not connected, and I threshold the matrix. This is not connected. I have a specificity of 1, but a sensitivity of 0. So it's not very useful, but it's just the beginning of the curve. And if I slowly decrease this threshold, you see the green dot appearing, which are the true positive, but also the false positive in red. And at this point, the green points are appearing faster than the red points, so my sensitivity increases while my specificity is not going down so fast. And the optimal point is in the middle here, where I'm maximizing, or let's say one of the ideal point is this point where it's maximizing specificity and sensitivity. And at the very end, I essentially say that everything is connected. And if I do that, I will be right in many cases. All the green points, all the green points will be correctly identified, but of course I will have a lot of false positives. All right. So if we do that now with the state-of-the-art tractography algorithm and build those curves, we see a couple of patterns that emerge. And many of the state-of-the-art tractography algorithms do very well on this data set with a good classification, a good prediction of what is connected in the monkey brain. And there's other set of tractography algorithms that we call deterministic tractography that perform slightly worse. But overall, tractography does a pretty good job of identifying what is connected and what is not connected in this part of the monkey brain. And this is just a summary of those connectivity at different threshold of the connectivity matrix. But again, you can see that some group of methods perform better. See here, the higher the value, the better the prediction is. So we were very happy to see that most of the probabilistic approach do pretty good job at predicting connectivity. And this is an example of what a prediction might be with a threshold, with an optimal threshold in this case. So you see mostly green, so all good for tractography. But obviously there's some mistake made by tractography, and this is the single biggest false positive that all tractography found. So it's a bundle that connects area F2 to area S1. So this bundle does not exist in the monkey brain. But we can also, if we look around those regions, we see two bundles that do exist in the monkey brain, and that was also very well recovered by tractography. This bundle connecting F2 to M1 and M1 to S1. So you can imagine already that if you have those two bundles that converge here and connect to M1, you have this kind of bottleneck type configuration here where the direction of the model converge. And if you think of a propagation algorithm that step locally on the direction, you can imagine tractography wrongly following first the blue bundle and then stepping in the green bundle and connecting to the other area. So at least that was one explanation for the presence of this bundle that was very large, very real looking, but not existing in the monkey brain. Another example here is the bundle connecting area F2 to area 8A. And there's another true positive connecting F2 to 8B, which is just a neighboring region, and a third bundle connecting area 8A to area LIP in the more posterior part of the brain. Same thing here, you can imagine the streamline of tractography starting from 8A here, going down and this below the sulcus where all the bundle here converge, and then wrongly following the blue bundle and forming this red bundle here. So a lot of overlap between those true positive bundle and likely the source of this false positive. So it was very nice to see those bundles in the monkey brain, not just on synthetic data from the challenge. Another type of mistake that tractography made was the false negative. These are harder to visualize because tractography failed to reconstruct those connections that do exist. But here we can see a couple of red lines. These did not survive the thresholding step of tractography, so it was wrongly classified as not connected. But if you look around in the white matter, there's very large true positive connections that do exist. And again, you can imagine tractography having trouble getting out of the pathway of those bundles, and most seeds or more streamlined failing to reconstruct the long, narrow bundle corresponding to this region connecting area 12 to PFG. And so just some concluding remark on this work. Tractography show very good agreement with track tracing. We have twice the number of true and false positive, 4 times the number of true negatives than false negative, and on average, 70% of the streamline were showed proper endpoints in accordance with the track tracing data. Obviously, some pathway are of questionable location, but the endpoints were correct. And overall, probabilistic tractography approach performed better than deterministic approach. And for a given sensitivity, the specificity is comparable or higher. And there's no large difference that we observed using more advanced techniques that use anatomical prior or do microstructure informed tractography to try to filter the false positive. Overall, all the probabilistic approach gave comparable results. And one of the conclusions of this work is that white matter orientation, voxel-wise, is not enough. We need additional feature to guide tractography and disentangle the bottlenecks and the merging bundle. And tractography create very real-looking false positive streamlined bundle in the monkey brain, as I was showing earlier. So that was a very positive result that we got on this complex network of the monkey brain. And then we were interested in challenging tractography in a more controlled environment where we have synthetic data and rich signal from Monte Carlo simulation. And we did this challenge in 2001 at MICAI called the Diffusion Connectivity Challenge, a disco challenge, and it went pretty well, and very interesting result came out of this, and I would like to share some of those results now. And the motivation for this work was based on the existing phantom that we have for tractography and microstructure. We have physical phantom that we can put in the MRM and then get the signal. It's a real signal with the artifact, with the real sequence. It's a rich microstructure property from the material that the phantom is made of, but these phantom are hard to make, and overall they have a simple geometry, so not really suitable for connectivity validation. On the other hand, we have complex synthetic phantom, like the one of the ISRM 2015 challenge. These are complex. We know exactly the ground truth. We can play with the MRI parameters, but overall, they have generally poor microstructure property. They are model-based signal, and they have a limited realism, let's say, in terms of signal and complexity at the microstructure level. But on the other hand, we also have the microstructure imaging phantom, which are typically used to validate a complex microstructure model, but typically at the voxel, at the few voxel level, often substrate derived from histology. And these can be obtained using Monte Carlo simulation and a complex substrate. And we thought it will be interesting to bring this information, but at the scale of a phantom that can be used for tractography and connectivity. So we tried, and we started with a connectivity matrix on a 16 by 16 region of interest, so 16 regions at the surface of the sphere, and we initiated a variable number of strands of tube that correspond to the intensity of this initial matrix. So at this point, we just have tube that merge and go in the middle of the sphere with no let's say realism in terms of microstructure. But then we start optimizing the position of the strand to remove overlaps, penalize length and curvature, and get something that is getting more and more interesting in terms of complexity of the tissue. We resample those strands by a factor 7 to increase the number of streamline, and now having multiple bundles of tubes. Continue the optimization until we reach 12,000 strands at this time sample from a gamma distribution, ranging from 2 to 6 micrometer in diameter. We did the final step, and we get this phantom where most of the tube are not overlapping and respect some have nice smooth trajectory, but also not straight lines. And this is how the mesh look like if we zoom in and then out. So it's a very large phantom for Monte Carlo simulation. It's 1 millimeter in diameter. We have 12,000 fibers, and we did add an extra layer of myelin, so reducing the intraaxonal compartment to 1.4 to 4.2 micrometer in diameter, and overall 26 bundles forming the connectivity. We did the Monte Carlo simulation and create an image volume of 40 by 40 voxels. And we also selected a very rich and complex diffusion MRI protocol for the challenge. And we did it 3 times, so we have 3 different phantom that we can give to the community and ask them to predict the original matrix that we used to build this phantom. And they did. 14 teams submitted the results for 111 connectivity matrix. And so what you see there is the best submission of all the teams. You can already see that the ground truth is very close to the submission of the teams. And we use a Pearson correlation coefficient to compare those 2 objects. And most of the team managed to get above 0.95 with the IS of 0.97. So extremely high correlation. So the team managed to find the proper weights of the ground truth connectivity matrix. Here, the weights was proportional to the number of tube interconnecting the region. Also looking at the fraction of valid weights, or in most cases, the fraction of valid streamline. The teams managed to get above 90% in most cases, with two teams standing out with 100% of the streamline in pairs of region that were connected in the ground truth. So that was quite impressive, and that although the phantom looked complex, the team managed to get extremely good result from this. And this is an overview of the best submission of all the teams, and you can see that it's matched very well with the ground truth that is on the top left corner. And this is actually the winning team here with 0.97 correlation. Now, if we binarize this network, just to go back a little bit to the previous work, we have this in light green, we have the region that are connected, and in dark green region that are not connected, and in bright red, the false positive, and in dark red, the false negative. And as I mentioned earlier, two teams got 100% of the weights in the region that were connected, so they have no false positive connection at all. But they have, of course, a couple of false negative, and three teams have only 3 false negative. It's a little bit hard to see on the projector now, but they have the 3 false negative, and they also have the same false negative, which was quite interesting as well. So those 3 teams managed to find all most of the true positive, missed 3, and those bundles were the same for all the 3 teams. And now what we did is to look at across the 111 submission, which pairs of region were falsely connected. So here's a false positive. So many teams, around 80 teams, found that region 4 was connected to region 6, and that region 11 was connected to region 5, I believe. So that showed that these bundles were easily tricking Tractography into thinking that these regions were connected, so to speak. So for the false negative, these are bundles that were missed by the team, by the submission of the team, and you can see that 3 bundles, these are symmetrical, but 3 bundles stand out that were systematically missed by most of the submission, even 1 bundle that was missing by all of the submission. So we look a bit closely what's going on, what happened with this bundle, and these 2 false positive bundle happen to be regions that are close to each other on the sphere. And if you look with your eyes, you can see that the direction of the ODF, of the ground truth ODF here, kind of make you think that there's a bundle here, but likely there's a bundle going up in this region and a bundle going down in that region. This is also 3D, so you have a region all over the place, and Tractography cannot disentangle this complexity at this level. And because these regions are close, they tend to form streamline very frequently, and then it's identified as a connection in the matrix. For the false negative, these are the bundle, and if you look at the bundle green and red, these are the 2 smallest bundle with the smallest connectivity in the data set, and these were often missed by the teams. And these 3 bundles, which are the 3 points I was highlighting earlier, they also have a particular shape. They go through the middle of the phantom, where's the complexity of the phantom really, and this is where Tractography fails to find the full path of those bundles. So to sum up on this section, overall 89% of the streamline had valid endpoint across all the submission. The correlation was on average 0.95, and with the winning team at 0.97. And the best, or most of the best performance was given by probabilistic Tractography again, but this time combined with microstructure informed Tractography. But there's also other pipelines that are completely different that gave also good results. So there's several diffusion pipeline that can give you a good approximation of this on this kind of data set. And most of the team denoise their data and use multi-shell, multi-tissue CSD to obtain the fiber ODF here. Plus, they also use microstructure informed Tractography to weight the connectivity matrix. The other thing is that, as you saw, the false positive and the false negative are not just random noise in the prediction. They are very similar across submission. Again, highlighting some complexity that Tractography cannot handle properly, like likely bottlenecks and narrow long bundle that tend to be underestimated by tractography method. So the final part is on evaluating the connectome, but this time in vivo in human. This is a work that was led by myself and Dr. Philippe Koch, and it was a collaborative project between Professor Girard, Professor Kunel, and Dr. Huber groups on this. And for this, we did acquire a lot of data. We selected a multi-shell MRI, diffusion MRI protocol at 1.6 millimeter isotropic voxel size. We asked 20 subjects to visit 2 sites in Geneva and in Sion, both equipped with the same Siemens 3D Prisma scanner. And each subject went twice to each site for a session, MRI session, and at each session, they did 2 repetitions of the same protocol. So we end up with 8 diffusion MRI dataset per subject, but acquire all of them within 2 months, and a total of 160 diffusion datasets in total. Then we did the state-of-the-art tractography and connectivity pipeline using multi-shell multi-tissue CSD. We use a matrix IF42 with 10 million seeds, and we used a free surfer distillery atlas with 163 regions to build this connectivity matrix. And the weights here is the proportion of streamline in each box, for each pair of region. So it's kind of a standard way to build the connectome. And now we look at the connectivity matrix for the population for our 160 subjects. And we expected that the difference in theory should be 0 between the 8 time points or the 8 data set of the same subject, because the brain is not expected to change very much in theory. But we expect some differences between subjects. We don't know how big this difference should be, but there should be some difference between the connectome for the technique to be useful, right? So to compare the connectome, we use this Breaker-Test dissimilarity index, which is just a sum of the absolute value of the differences between all the region of each of the connectome. So the sum of the absolute value of the difference normalized by the total value of the 2 connectomes. So this gives you a value between 0 and 1. 1 meaning that the connectome are identical, a 0 if the connectome are identical, and 1 if they are completely different. And this is the result for the 20 subjects. So what you have on both axes is the 20 subject, and for each subject you have 8 MRI dataset, and the intensity of this image corresponds to the dissimilarity index. And so what you see on the diagonal, the blue square, are the intra-subject dissimilarity, so the difference between all the connectome of the same subject, and what you see off diagonal in green and yellow is the difference between subject. And overall, the intra-individual dissimilarity is 0.08, but the inter-subject dissimilarity is 0.20, yielding a ratio of 2.32. So meaning that on average, you are 2.3 times further away from someone else than yourself, if you repeat the process, which was an interesting observation on this data. Another thing that we found out is that the subject identification is 100%. What I mean by that is that if you give me one data set of all the 20 subjects and an extra data set, in 100% of the case, I can identify the subject looking at this at the distance of the connectome. So the subjects are very well clustered in this space of connectivity, which was not necessarily expected, but turned out that it is. So it's in this data set with this protocol and this pipeline and 20 subjects, the connectome estimated with diffusion MRI is a very good fingerprint of the subject. We also look at the variability, the source of variability in this project, and it turned out that the variance in the connectome within the subject, the variability within the subject connectome, 70% of it come from the repetition of the MR itself. So just the noise in the MRI and the accumulation of error in the pipeline. 20% come from changing site from Sion to Geneva, and 10% from changing session within site. So most of the variance is really related to going in the MR and doing the acquisition and adding some different noise in the image. As I mentioned, the connectome are very good to cluster the subject. And something I didn't add in the last slide on this, but the tractography error seems to be reproducible and also subject specific. So your bottleneck error also are a property of your brain somehow, which we found that was quite interesting to see. Again, showing that bottlenecks is not random noise, or tractography error rather, or is not random noise in your connectome. It's something that is specific to the shape of your brain and to the data. So it's a limitation of the tractography algorithm that is systematic and always appear on your connectome. So on this, I would like to thank you for your attention, and I'm happy to take some questions on the three topics.
So my question is about the data in the macaque brain.
Mm-hmm.
So you know by those experiments that you have those two positives, and you know all these filtering techniques like commit or whatever, they assume that if you attach an analytical model to each streamline, then the signal is going to be deviated from the reality if those true positives are there or not.
Yes.
So what do you think? You can actually see a difference when the bundles are there and when you remove it, the signal is that different? Because in the case of the synthetic data like VISCO, of course, you impose the model from creating the phantom. But in the actual real data in the macaque, when you remove and put back the true positives, the false positives, you see a difference in the MRI signal.
Yeah, that's a good question. But the thing is that we only have binary connection there. So some of those bundles are very small, some of those are very big, and we don't know which one is big and which one is small. We know them specifically, but it's hard to put them together as a reference, you know, which we don't know the strength of those connections and the type of the connection. We could eventually think of using a commit, for instance, to remove some bundle and see how it changes signal as you suggested. But this will be dependent on topography and which input you gave. For this project, we didn't see that commit improve the binary prediction of connectivity, but it did when we used the disco phantom. It did also very well on the human and showed the result, but we also did this experiment with commit. So overall, I think the target, this binary classification, it's too easy for tractography somehow. It doesn't need the filter. It's too the change that commit gave to the data is too subtle to really change the classification of connected or unconnected. But it will be interesting to start with this data set as they did for ISMRM and now play with commit as a ground truth and remove some bundle and see how tractography behaves. Surely that will be a nice experiment.
Okay, thank you very much.
Yeah, thank you, Gav. So I have a question regarding the patterns of errors. Like, could this be, for example, that there are different patterns depending on the medium used, like if it's a physical phantom simulation or a real brain, like you have more false positive here or false negatives here, or you think it should be almost the same?
Yeah, I think it's very much data dependent, and that will be dependent on your phantom. I think we have a lot of bottleneck type configuration in the brain where, for instance, below the sulcus or the corpus callosum is probably the best example when everything converges and then tractography does not know where to go once it gets into the corpus callosum. And that's maybe one reason why tractography was doing so well in this part of the monkey brain. We didn't have the corpus callosum included, with fewer bottlenecks. But if you imagine a synthetic data set or a phantom where you only have crossings and not so many overlap, I believe tractography will perform extremely well in this case, at least with respect to this problem. But overall, I think it's a problem of our algorithm that are not good enough to deal with all the algorithms I've been showing are really step-by-step algorithms. So they have the greedy algorithm that takes the best step locally. But we need to develop better tractography algorithm that will look ahead a little bit or learn from the previous step what type of bundle they were following. And I think these type actually I did develop tractography algorithm in my thesis, and I was facing problem in validating those algorithms. And this type of work was to give the community also tools to validate tractography and help the development of tractography. And I think these are good place to start and to develop new tractography algorithm that will look further than a few millimeters ahead or behind.
One more questions? Is there any question online? If you are unmute, light on the camera. Okay, let me look over that.
There is one question. Maybe I can read it out.
Yes, please.
So the in silico phantom is very pretty, but I've never seen an area of the brain with such strange configuration. Wouldn't it be better to have a phantom resembling the brain's white matter bundles?
Yeah, a good point. We didn't design the phantom to look like a brain. It will be a nice extension actually to try to have a shape that is more similar to the white matter. That was one of the criticisms that we received, but really what we wanted to do is to have this, the middle of the phantom was really the area of interest for this phantom, where we have this merging, crossing, and intermingling configuration of bundle. The outer part are really just to make validation and testing easy, so we know where the bundle goes and we can clearly identify true positive and false positive. And so, of course, yeah, the phantom doesn't look like white matter, but with that, we have example of complex configuration, and that we can also simulate with Monte Carlo simulation and nothing a mesh like this one. But yeah, I think the next step will be to, I think there's two directions here: increase the complexity of the microstructure of those phantom, just making it more realistic in terms of local microstructure, but the other aspect is to make it more realistic in terms of macro organization of the fascicle and better match with the complexity of the human brains.
Any more questions? Please. There's no more questions, and thanks.